Okay, so Dr. Anupama Ray is an advisory research scientist at IBM Research India. She is an IBM Quantum Technical Ambassador and a Qiskit advocate. She completed her PhD from Indian Institute of Technology, Delhi. Her doctoral research focused on developing and applying multidimensional deep recurrent neural networks for document analysis and computer vision applications. At IBM Research, she has been predominantly working in the area of natural language processing, building NLP systems for low resource languages, domain independent information extraction systems, and natural language generation. She is currently working in the area of quantum machine learning and quantum applications in finance. She has published several papers in top tier conferences and journals and has received several Best Paper awards. She has been the recipient of the IEEE Best Woman Professional Early Career and Technology Rising Star Award from WOC STEM Awards. She received several awards at IBM Research, such as Research Division Award, Eminence and Excellence Award, and Outstanding Technical Achievement Award, to name a few. She was nominated and selected as a Young Scientist in Global Young Scientist Summit and is an active member of IEEE, AAAI, and Society of Women Engineers, India. So thank you so much, Anupama, for agreeing to give this talk. So just one announcement to all the participants. Today, Dr. Anupama Ray will take both the lecture and the hands-on session. So she can divide the time whatever suits best for her. And as usual, we will give two attendance sheets, one during the lecture, the one during the first hour, and the next during the second hour. And you have to fill both of them. So thank you. On to you, Anupama.
Okay, so let me now share my screen then. Let's get started. So you guys might have realized I have like a very mixed background. I've been doing quite a lot of things. Let me just hide this from the screen. Will my camera remain visible? Is there a way to?
Yes, it's visible.
Yeah.
Yes, yes.
Okay. No, let it not be visible, at least on my screen. Okay. So I hope you guys are having a great Qiskit Fall Fest, and thanks to Ritojit and Devashmita for organizing it, and of course thanks to Vishal. He's always there in any Qiskit event that I am seeing, and I'm very proud of him. Yeah, I had my first interaction with Vishal. He was my TA for my first NPTEL course, and he's an excellent person. So I know that all of you must be having a great time in this Fall Fest with three very active mentors. All Ritojit, Devashmita, and Vishal are very active, very passionate about quantum, very knowledgeable in this field, and I'm sure they must be giving you guys a great time. So today we are going to talk about quantum machine learning, and I'm going to try to cover things that will help you in your hackathon as well. Okay, so let's get started. So what the plan for today is, I'll just briefly introduce you on why quantum machine learning. There's a lot of buzzword quantum, people really there's a lot of interest in quantum machine learning because there was a lot of interest in machine learning and now in quantum computing, and people see a very natural intersection. But there is actually a reason why this is important. So maybe why quantum computing is very clear to all of you, and you guys are already very motivated to learn about quantum computing, and that's why you guys are here. But as we know that there are a set of these very complex problems that we can't solve with the laws of classical physics, and that's the reason we go to quantum physics laws. And classical computers don't work around with quantum physics laws. That's why we needed this paradigm shift, and we wanted to shift gears and work on this kind of a computing platform, right? So why quantum machine learning? So in machine learning, there are a couple of very interesting problems, and we'll see what is that overlap with machine learning and quantum, and why do people get so interested in this field of quantum machine learning. Of course, we'll discuss a bit of the current challenges and what are the open research questions. I'm assuming many of you might be research scholars or PhD students, and you would want to look at, how do I apply, where do I apply quantum machine learning? What are those kind of active problems that have that not so dense research space, and there's a lot of open questions that we can answer. And we can talk about a couple of real world use cases as well while we are doing these algorithms. I'll keep mentioning different algorithms or different applications as well. But quantum, in our minds, we have these three buckets of problem areas where we want to apply quantum computing. One is simulation, for example, in high energy particle physics, or for molecular simulation, which is very important for computational chemistry, or for drug discovery, or protein design, and so on. Then the second place is optimization, wherein you have algorithms. Classically, you have algorithms like Markov chain Monte Carlo, and you want to have algorithms in the quantum space that can speed up MCMC, right? Or even other algorithms. And this is very, very useful for applications in finance. So typically in finance, in all of this portfolio optimization, trading, you have immense amount of data and all real-time predictions that you need to do on all time series forecasting or options pricing and so on. So this entire bunch of optimization algorithms find its use in not just finance, but in several other fields as well. And of course, then the third bucket is quantum machine learning, and we are going to talk about that in detail. So, just to say why even quantum computing. So this is a snippet of it used to be world's most powerful supercomputer. Now it is the second world's most powerful supercomputer, with the first one is from Fujitsu now. And this can also, but I have the liberty to take it because I'm from IBM, so I can use it and talk about it. So this particular supercomputer, or which we call Summit, so Summit can actually do 200 quadrillion calculations every second. So it has like 27,000 GPUs with it. It has Power 9 processors, which are extremely fast processors, and over 9,000 such processors. So it's a large device and can do things very, very fast. It was used, I'll give you an example. So when COVID just happened in 2020, and when chemists were actually struggling with this drug discovery problem and coming up with an antidote at that time was a concern. Coming up with a vaccine was not even looking like a reality in the months of January, February. So we put in a lot of data into Summit, and there were a lot of experiments that were run. And from a space of 8,000 chemicals or 8,000 molecules or 8,000 elements, and imagine their possible compounds, the search space was reduced to 64 compounds that could be useful to be able to capture the body or the surface of this COVID molecule. So that was done in a matter of 3.5 days, which would roughly take a chemist several years to do these wet lab experiments and find out, okay, each compound I apply it on that protein of COVID and see that, okay, whether it is being able to cover the surface completely or not. Right? So all that wet lab experiments could be completely reduced by these simulation studies that was done. I wouldn't say completely reduced, it was drastically minimized is a better word to say. And that search space of 8,000 plus compounds came to just 64 compounds. Right? So this is a major reason why we can actually speed up things like vaccine preparation or so on. Right? So there are still hard problems. That's something that we understand from this. Now, this chart paints a very good example of where these problems kind of lie, and we're trying to see from a classical and a quantum system angle. Right? So in the center, that the place that you see, the white ellipse, is problems we can very easily solve today. For example, if you have to multiply to, say, 2048-bit integer, right? You can easily do that. Or you have to read emails, or like we are streaming live videos. We can easily do this. Now, in the light blue area, which is a very interesting area to me, is there are these problems which we cannot adequately answer today using these classical computers. And they're generally problems that require very large amount of data, or very long periods of time, or sometimes even both. So, for example, in machine learning, and nowadays no one talks about, so people only talk about deep learning, which takes tons of data and has very long training time, even if you have access to plethora of GPUs and all, right? So it's mostly a combination of both, and that's the kind of problems here in this sky blue area, right? And even in the sky blue area, there are problems like factorizing large numbers, right, or simulating complex molecules, and some optimization problems are also in this space. But then this dark blue area, it's most interesting. So here are problems which we see that quantum computers can address, right? So quantum computing is not a powerful hammer. It's not just a bigger hammer for any nail, right? There are problems which quantum computers don't do well. So for example, if you want to multiply two 2048-bit integers, you can do it way better in your classical computer, so it will fall under this white area. But if you do a factorizing of the same 2048-bit integer, it would be a hard problem classically. And if you do the same thing in quantum, so quantum multiplication will take you more time than that of classical, because multiplication is a process which you can easily parallelize. So that you can easily do in your classical computing or classical hardware, versus factoring is something that quantum computing can do better, right, or can do much faster. So there are certain problems which we can actually do much better in quantum computers. And the most interesting part is this. So there were a couple of problems which we were not even able to touch before. So this is beyond the sky blue overlap. So this portion is those kind of problems which we barely could scratch the surface is what I feel. Right? So those are problems with high energy particle physics, or simulating bigger molecules. For example, we talk about hydrogen molecule simulation, right? So that is a toy example. Think about larger problems. Think about, for example, RDX, right? So what we do with RDX today, we just have blasts, right? Because we don't have any way, we don't even know what to do with RDX. We don't know how to control the amount of energy that it can radiate, right? So what actually happens is, if there is an impact on an RDX, say a molecule, it initiates a series of chain reactions, right? So what do you do with these chain reactions? So you will try to have, if you had some control over these reactions, then you would be able to have an energy production, and you could use it for much bigger problems, wherein you can use that as a renewable energy source. So I'm just giving you bigger examples just to motivate why we need to do on this. Now coming to why quantum machine learning, right? So machine learning and quantum computing have a huge interplay of ideas, right? So there are a number of ways where machine learning scientists actually look at quantum computing. So one thing is, of course, modern day deep learning succeeded with these parallel GPU clusters, right? So neural networks came into the big picture in 2012 when these parallel GPU clusters were functional. So of course, people feel that quantum machine learning will just extend this pool of hardware for machine learning, and with an entirely new type of device, the quantum computer. So you will have additionally your GPU cluster, your classical computer, and your quantum computer. So you'll have everything together, right? So it will be an addition to the pool of hardware access that you could give your algorithms to. That is one. The second is, you have what is the commonality between both? Linear algebra, right? It's common in both. So they are both algebraic things, and they both function in linear algebra. The third thing which is very interesting is, whenever we talk about quantum computing, people actually crib about noise, right? So we constantly say that this is a noisy intermediate scale quantum, or this is a NISQ era, as Preskill coined it. Or we talk about, okay, noise-free systems is something that I don't know when it will come, right? There will be a bit of noise maybe for a very long term, and that's the reason why the biggest research area in quantum computing is actually noise correction or quantum error correction, right? But machine learning, on the other side, is very happy with the noise, right? So in machine learning algorithms, or if you talk to machine learning researchers, they'll say that, okay, noise is good. Noise gives me an ability to generalize. So if there is noise in my data, or if there is noise that my model has, then my model is not going to overfit on my training data, and it's going to learn something. We have models, for example, we have generative models like GANs and all, wherein it starts with noise. The input to the algorithm itself is noise, and with noise, it's trying to hallucinate and generate some probability distributions, right? So noise is not an issue for ML, and noise is a friend of ML. So if there is noise in the current quantum hardware, we are most welcome. We can still do some work, right? The fourth point is, there are multiple goals. So if you are looking at a quantum advantage perspective, that, okay, can quantum make my machine learning algorithms better? In what sense are you talking about making it better? What is the sort of advantage? So in machine learning, there are several aspects. You can have improvement in terms of accuracy or, in performance. You can have improvement in terms of space-time complexity. You can have improvement in terms of explainability. And why do we say that? So modern day deep learning algorithms, they are experimentally excellent. They are working very good. They lack theory. On the other hand, quantum algorithms, they are very theoretical grounded, but they are not performing very well due to, the hardware is nascent or the technologies are pretty new, and they'll take some years to mature. Machine learning has been here for last 40, 50 years. Quantum machine learning is just a 5-year-old kid. Quantum is here for several years, although. So quantum machine learning will take its own time to mature and have, better sophisticated algorithms. But till then, we still see that there is something that machine learning doesn't have, which is theoretical grounding, which is excellent in quantum. And quantum doesn't have experimental evidence, which is excellent in deep learning algorithms. So there should be ways that we can, leverage the best of both worlds, right? And of course, differential programming is the basis of deep learning. It is something that is inherent in a quantum computer. An entire quantum computer can work as a neural network. So you can actually do. So if you talk to quantum control people, they'll say that okay, it's an entirely differentiable machine and so on. Now, what are the challenges and open problems? So just to paint that, I have this little, confusion matrix kind of a symbol here. So let us think that you have your type of data in your y-axis and your type of algorithm in your x-axis. So you can have classical data and classical algorithm, which is sort of the classical machine learning things that we do. You could also have these classical data and quantum data and still apply classical algorithms. So that is typically what we were been doing. So whenever we have some quantum data that we measure or measuring outputs, and then before you measure it, it still remains quantum, and you want to have these or for mostly these physics kind of problems where you have the spin systems and you are applying some classical machine learning techniques. Today we are going to focus on this quadrant, which is I have classical data, however I am applying quantum algorithms. So I am applying quantum machine learning algorithms on classical data. So that is the segment that we are going to focus on today. And then of course, where we really feel there is a huge potential of advantage in where, where it is, where the data is also quantum native. So the algorithms are applied to a data because the data inherently has, say, a high amount of entanglement or properties that cannot be classically coded, right? So there are several such problems in chemistry and physics and in bioinformatics, wherein if you apply classical algorithm, it's a known thing that if you apply classical algorithm to such a data, you're going to lose most of the information, right? You're going to lose the entanglement or all of that. So now coming to what are the problems. So of course there's a problem called barren plateaus, which you might have heard about. But barren plateaus is not something which is exclusive to quantum machine learning, right? It is something that is there in even machine learning and deep learning, right? So whenever there is a loss curve and you're trying to learn something, there is so barren plateau is typically what we call as large regions of the cost function where the cost function parameter space variance or the variance of the gradient is almost zero. So it's like a flat landscape of the cost function, right? So wherever it is flattening, it is not being able to learn better, it is getting stuck in some local minima, is where we say that okay, this plateau after that is the barren plateau, right? And that can happen in any of, both of these places, right? But what it means is that the variational circuit initialized in one of these areas has become untrainable using these gradient based algorithms. So there are ways to in which you can overcome the barren plateaus. Okay. And of course, there are different other open problems. For example, how can we benchmark quantum algorithms? How can we make quantum algorithms run on larger data sets? So on hardware, running on larger data set is still a challenge, right? So how can we do that? Now, another problem is given there's a large amount of, there are systems. So IBM is coming up with their 433 qubit machine, maybe by December, right? But you are still running on smaller circuits. So what is the best way that you can use the entire 433 qubits, right? So there are different other problems. Of course, then state space encoding is a problem. So whenever you load classical data into quantum states, that's called encoding. And we're still trying to come up with better mechanisms of loading classical data to quantum states. Then, there are, how can we get classical solutions which are encoded in quantum outputs, and several others. And we're going to look at a couple of these or some solutions to some of these problems today. So the two algorithms that I plan to cover, and how am I doing on time? Okay. So the two algorithms that I plan to cover are variational quantum classifier and quantum support vector machine. Okay. And I'll give you a bit of intro, and then we'll actually look at the math of this as well. So let's think.
Anupama, can I just ask two questions that have popped up?
Yes.
So the first is Shomodeep is asking what particular factor, if there is one, that decides that the problem is beyond the purview of classical computing. I think this is with respect to that chart you showed.
Yes. So there are several actually. It sort of depends. So so entanglement is one such quantum phenomena that cannot be mimicked classically. So when you're working on, fermionic systems, okay, fermionic systems is basically where you have electrons. So you're working on electron systems, and these electrons are correlated. Okay, so these correlations cannot be captured classically. So those are problems that classical computing cannot do. Then you have problems, for example, there's a concept called quantum tunneling. So at a subatomic level, the classical physics doesn't work. So classical physics work till that atomic level. So what happens in quantum tunneling is basically, let me give you a different analogy. So you have a ball and you hit the ball on a wall, and it bounces back to you, right? But when you play around with subatomic particles, it can just go through the wall, right? So that is called tunneling effect. Now there are classical physics sort of, we can't go beyond that. So those kind of effects can be governed only by quantum physics. So these problems inherently we can't even do classically. Now coming to the other part of your question, so what is that point beyond which the classical computer can't work, right? So there are several such examples also, and given the example of RDX, right? So what people right now do is they will break down the RDX molecule, and they'll form smaller parts of it, and then they'll try to have a ground state estimation or a excited state estimation of the parts of the molecule. Now when you do it on parts, you're being able to do, because you have less number of states, so you can do it on parts. But then when you sum it up, the properties that are exhibited by these parts are not the properties that are exhibited by the sum.
Hello.
Yeah, can you guys hear me?
Yes.
Okay. Yeah.
Any problem, Ritaji?
Hello.
Yes, Ritaji.
Did we lose Anupama?
Oh no.
I can hear you guys. I can hear you guys fine. Can you guys hear me? Vishal, Debushmita, can you hear me?
Yes, we can hear you.
Yes,
Okay.
Anupama.
Maybe some issue with Ritajit's connection. Okay. So yeah, coming to that exact point, so it is very hard to kind of pinpoint and say that this is a point beyond which a classical algorithm won't work. Now, given in quantum machine learning setup right now, the problems that you are seeing, they are all working in the space of classical machine learning. It's just that it is taking a lot of time, or it is taking a lot of compute resources, or it is taking a lot of input data to be able to get you the results. Now, can we come up with a proof of concept? Forget advantage as of now. Can we at least come up with a proof of concept that there exists a quantum machine learning algorithm which can do it better than the current classical algorithm? And that's what we are going to look at. I'll try to motivate and give example of one such quantum kernel which theoretically shows that kind of an advantage that is achievable by quantum SVM, right? Makes quantum SVM much powerful than classical SVM. So we'll come to that. Yeah? What was the second question, by the way? I can't. Okay, now I can see chat. So
Okay, the second question is how big dataset is possible to run in quantum computer nowadays with respect to classification using machine learning?
Sure. Yeah. So that's a more grounded question. So if you are using something like a variational quantum classifier, which we are going to look at today. So if you have n data points, it is going to create n such circuits. Okay. So n circuits. So it's like linear with the number of training data. So if in this case you in a simulator you can run as many training data as you want. However, in a real hardware the challenge comes at this level. So you have n data points, you have n circuits. Suppose you want to run on a smaller machine, these open access machines that you have of mostly 5-qubit machines, they can run each circuit job with, one job can have 100 circuits. Okay, so then you can run say a couple of jobs and say maybe do up to say 1,000 circuits, right? Then if you have a higher order machine or access to a higher order machine which is like say a 27 qubit machine, or even a 16 qubit, Guadalupe also has it, 27 qubit machine or 127 qubit machine, they typically each job can run 300 circuits. So the same amount of training data, you can actually run way more number of jobs. You will have to run way more number of jobs in a smaller machine versus lesser jobs in a larger machine. Now the problem is not with the data. The problem is when you have these job scheduling, these jobs end up in some queue time, right? So they are all running on the quantum computers are sitting somewhere in US, right, in Poughkeepsie, and you are running them through cloud. So your queue, your job is on hold and on some queue, and you run one job and complete, and then the other job and complete, and so on, right? So the overall wait time becomes so long that you say that, okay, beyond say 1,000 data points, I'm not being able to run in a meaningful amount of time. I'm not being able to run these quantum algorithms on current hardware. Right? And this is what I'm talking about, IBM hardware. So because that's openly available, there are a couple of other hardwares also with different technologies, but they have their own pros and cons. So not talking about that. Any other question, Devashmita, you see on chat?
There are two more questions. One is what is quantum data, and another is how to understand which problems have faster solutions in classical and which are in quantum.
Yeah. So there are a lot of literature for that. Okay, I'm answering the second question first. There's a lot of literature on this, that what is better classically and what. So for example, multiplication is better classically, and the same numbers factoring is harder to do. So basically, it boils down to the field of computational complexity. So if you understand computational complexity, maybe you guys would remember order of complexity, the big O notation. So if the big O notation is something in exponential, and I used to have a graph on that, maybe I should have showed that. So if you have problems which are of the size of exponential or even higher order polynomials, those are the kind of problems that you should give to quantum. And if you have problems which are linear or polynomial or sub-polynomial, those are the kind of problems which a classical computers can comfortably do, right? Now coming to the previous question was I forgot, Devashmita. What was the
What
previous?
is quantum data?
Thanks. So quantum data is data that is generated from some quantum, it could be quantum devices, it could be quantum physics, it could be some quantum generator. So if there is a quantum device and it is generating some sort of a data, or it is some experiment that you are running, so it could be some, say, boson sampling experiment, or some other physics experiment from which you are sampling that kind of a data, that is a quantum data. Versus what is a classical data? So for example, you have you have problems like image prediction. So you have cats and dogs images. So this is all classical data, right? So you can load this classical data and run on these classical data, or you have say discrete data, or you have even if you have some continuous data. So continuous and discrete data can also come from quantum sources, but whenever the source of data generation is a quantum system, or which is governed by the laws of quantum physics, we call that a quantum data. Versus if the source of data generation is classical, we call that classical data. Okay. So any more questions, or can
Yes,
I?
now you can continue.
Okay, so let's come back to variational quantum algorithms, and here, so think of this in this way. So there are few steps in order to create a variational quantum algorithm. What are they? So first, you are loading some classical data. So you have to load this classical data into quantum states. So in the previous or in the last week, all the lectures that you would have been through, those lectures you would have seen that there is some state psi which is expressed as ket 0 plus ket 1, something some with some magnitudes of that, right? So that state psi is a quantum state which you're trying to prepare. So state preparation needs to be done, and you have to encode your classical data into this quantum state. So that part is called data encoding, or and we'll go through a couple of that. The second part, or the second module in a variational quantum algorithm, is an ansatz, or a parameterized quantum circuit. So you have some circuit which has some parameters, and these parameters are what you learn given your data set and given your cost function. So what is your final end goal? So if you have an end goal of, say, cats and dogs recognition, so you first load these images into some form that they are now converted into quantum states in your data encoding step. Then you have some parameterized quantum circuit. It's called ansatz. Ansatz is just a German word for educated guess. So you have an educated guess. So you say that, okay, it's an image. So definitely convolution can work better. So let me create something which can actually do some convolution operation on my quantum circuit. So that will be your ansatz, right? And then after that, you will do some measurements, right? And once you do some measurements, you'll measure the values in each of the qubit, and you do it on some basis. So you can do it on computational basis or some other basis. And then you have some post processing, right? So you have some cost function, you do some post processing, and you say that, okay, okay, so this, if this is say like this, then it is a cat. If this is like this, it's a dog, or something like that. Now, if your image was a cat's image and you ended up with a dog classification, then you say, oh, it's my cost function says this is wrong. So now I want to go back and back propagate and learn these parameters. So I'll have to change the amount of convolution, or the multiplications that they are playing in that are happening in the ansatz part, that I wish to change. And these values I am going to keep changing in each of the iterations of my optimizer. Now, why is it called variational quantum algorithm? So I'll not go into the math right off, but one thing is that why are they called hybrid? Maybe I should explain. So why are they called hybrid algorithms? Because a part of it is going to run on a quantum processor, and a part of it is going to run on a classical hardware. So let's look at a breakdown version of this. This is for a variational quantum classifier. And here you see that this classical data is getting encoded to quantum state. So this is a quantum thing that we are doing. This parameterized model, or ansatz, so that's something which is quantum. And once you measure, it's all classical data. It becomes classical data, right? So then you can do the post processing, and you can do this optimization in a classical device. And this classical device can be just our laptop. So we are working on cloud. We are sending something on the IBM Quantum computer, which is on cloud. And then we are doing some optimization in our laptop, sending the next best parameters, again doing the set of, how much rotation should it do, or how much convolution should it do, sending it back, and so on. We are running each epoch. Okay. So a bit more details here is that, there are different ways of doing encoding. Although this encoding thing is an open research problem, there are several ways that have been proposed in literature, and of course this is not an exhaustive list. So we can do basis encoding, we can do amplitude encoding, we can do feature maps, and if I get time, I'm going to cover them in a bit more detail as well. But I'll just introduce the next algorithm before that. So the next algorithm that we're going to look at is quantum kernel learning. And I'm not sure how many of you have, classical machine learning background. So I'll quickly go over a couple of slides from, this is actually slides adapted from Quantum's Global Summer School 2021. So these slides in black, you would have seen them if you have attended Global Summer School. And these are very simple slides, though, so I thought that we can quickly introduce the concept of what happens in a classical SVM. So suppose you have you have a data set which is a two-class data set. So you have some data points belonging to class 1, some data points belonging to class -1, and they are represented by these dots here, sky blue and light blue. And given a new sample, you don't know what is the color of this sample. You have to either put it to this class or that class. So what do? You kind of create a hyperplane, right, or draw a line in between so that you can easily distinguish. So if the distance between this point and the hyperplane is lesser than this point and this point, so you say that, okay, it is in this class. And what you basically do is you can think of this in several ways, but I just say that, okay, so this is the maximum, this is the sort of a margin that you're trying to create, and what you intend is you want to have this max margin as the maximum. So what is that maximum margin that you can create in order to have a clear distinction between the two classes, right? And the points that are lying on these margins, they are normally called the support vectors. So they are the ones who are supporting the decision that you take for at a prediction time, right? And what is the advantage of this algorithm? So you don't need to actually compute the distance of this point with each point to find out whether it is closer to this point or whether it is closer to that point. Or you don't need to do it with the centroid. You will actually just compute the distance of this point with this point, this point, and this point. Then on the other side, you will compute this point, and this point. And whichever is smaller, you say, oh, you belong to that. Okay, so I'm just giving you an intuition of classical SVM, but yeah, there are very good resources. You can actually follow Andrew Ng's Stanford lecture. I forgot this course number, but if you just search Andrew Ng classical SVM, that's the best source to learn about classical SVM. Now, there are some data sets which are linearly separable, as we saw in our previous slide, but there are some data sets which are non-linearly separable. For example, here you have this which is like non-linearly separable. But what is a good way to separate this kind of data? For example, think I push this or I pull this sky blue line here, right? So now these go up and this goes back. So I can still create a sort of an elliptical curve or an elliptical hyperplane here, which says that, okay, all the dark blue lines are on top of the plane and all the sky blue lines can go bottom of the plane. So when I'm doing this kind of a transformation, wherein I'm pushing this, all the data points which had this small sky blue line, or I'm trying to have a distinction between these feature spaces, that is called a feature map in terms of classical machine learning, right? And this is just done whenever there is linear separation is hard. We say that, okay, if we take it to some higher dimension, if we push it to some higher dimension, maybe in that dimension, the problem becomes linearly separable or at least easily separable, right? But most problems are not linearly separable, and that's what you'll see. And this concept of feature maps is going to be very, very important something, right? Now, what we are doing in the space of quantum is we are actually just trying to fit in this sort of a feature here, and we are saying that, okay, I'm not sure if you know this equation. So in SVM, we can actually pose it in the form of a primal and a dual, and we'll see that, okay, SVM is a convex optimization problem, right? So either it is minimizing the primal or it is maximizing the dual, right? And minimizing the primal is equivalent to maximizing the dual. But what is the change that we do? So instead of calling it as a similar, so what is a kernel? Kernel is just the you can consider it as a similarity measure, right? It could be a distance metric, as we explained in the previous slide, but it could be anything which can denote some sort of a similarity between the two data points, right? So the data points could be xi and xj, and what is a good way to show similarity? So k of xi xj is just trying to encode that, okay, maybe what is the distance between xi xj, or what is the similarity between xi xj. Right now, what are we doing here? We are actually transforming this portion when we talk about quantum SVM. We are just saying that this is, instead of k of xi xj, this now becomes phi of xi xj, wherein this is an inner product and this is an inner product. So we are now trying to take the inner products of two feature maps. Okay, so a major advantage of this dual formulation is if we can evaluate the inner products, then rest of it is trivially just a convex optimization, and that can be solved by any of these off-the-shelf softwares, right? So what we do is, and we are going to see that in the lab, that we are going to use this classical SVM and use classical SVM as just the optimization portion, and there's just this kernel computation. This kernel part we are going to do it in a quantum computer. So rather than organizing all inner products in a kernel matrix, so you don't have to put in or compute each value in that kernel matrix. So each entry, which is this ij entry, now this entry is just the inner product between the ith feature and the jth feature. So it's a symmetric matrix, and there are a couple of properties which I'll not go through, but it has to be positive semi-definite, right? So the key insight here is that inner products are scalars, so we can solve this optimal hyperplane problem without ever actually computing any of these feature vectors. So you don't need to know how to compute phi of xi, but you can just do the inner products and you can create this kind of a kernel matrix. So even if you have thousands or say millions of features, and imagine if you had to actually fill in the kernel matrix and you had to do the compute and for each entry, then you would have that 1000 into million number, right? That would have been very computationally expensive. But with this assumption, you can do these inner products much faster. And this is called kernel trick in general, right? So we'll just leave it here. So the main thing is here. So this kernel Kij, which classically we wrote as K of xi xj, we are now being able to replace with an inner product of these two functions. So this replacing a kernel, what happened? Yeah, replacing a kernel with another kernel is called the kernel trick. Okay. And this is a very common kernel, this is RBF kernel, but in the interest of time, maybe I'll skip it and show you how it really works in a quantum support vector machine. So again, the same sort of steps here also. So you have the classical data, you do some pre-processing, some feature extraction. Then you use this quantum kernel matrix. So you want to extract this quantum kernel to be able to project this data to some higher dimension space. You train this SVM model, and this could be your classical SVM model also. We'll see how can we use a classical SVM, how can we use other models, and then you will do some post-processing. Right? So this is typically your this K of x of xy. Now here you're parameterizing it with something called a lambda, and that's the reason if you parameterize it, then you can learn these lambda values over time. So this is an example of a forelation kernel, which is one kernel which is very hard to compute classically. And often you will read this that in order for quantum kernels to show a quantum advantage, the kernel has to be hard to classically be simulated classically. So it cannot be simulated easily in classical devices, and those kind of kernels will typically give you value. While this is a necessary condition, it's not sufficient, right? It's not sufficient. It does not guarantee you a quantum advantage. The reason being that it could be something which is very hard to do classically, and it can be done easily in a quantum hardware. But that does not guarantee that it's going to work well on the given data set that you are working, right? On a given the classification problem that you are working, right? So so here I'm just going to stop on these set of slides, and maybe a few minutes I'll spend on a couple of these things, and bear with me. These are my class notes. So normally I take a course on quantum machine learning, and these are my class notes. So I thought all the math can't be put in PowerPoint, and I'll go over, but I'll not go into too much math. I'll try to have a high level so that you guys understand all the concepts, because I'm packing in a lot of concepts in the same class, right? So what happens in variational algorithms? We spoke that, okay, you have a state preparation, so you have a feature encoding, classical data loaded as a quantum state, and then you have some unitaries or some parameterized quantum circuit or ansatz, whatever you call it, which is parameterized over some theta parameters, and these operations you apply. Okay, sorry, I don't think you guys are seeing my screen, right? Now you guys should be able to see my screen. Do you guys see my screen now?
Yes,
Yes,
but
yes.
not full screen, I think.
Yeah, I was trying to.
Yeah, maybe you can zoom out a little.
Yes, yeah, I'm just trying to do that so that the side things are not something important, but you should be able to see what I've written here. Okay. So now what do we do is, yeah, ansatz and PQC are the same. I could see someone's chat. Okay, so sorry guys, I was not being able to see chats still now because I was doing this slideshow mode, but now I'll be able to see. So maybe we'll take some logical gaps and we'll try to answer questions. If there are any questions, maybe we can spend 2 minutes and answer some questions now, and or maybe we can do some after some time. Okay, so let me cover a bit more theory so that I get some time for the labs as well. Okay, so I'll try to cover a couple of things here. So in a variational quantum circuit, what happens is you have this ansatz, and then you have these theta values, and what you're trying to do is after this measurement, you will have some outputs, and you're trying to optimize these parameters theta. Right? So in a classical machine learning framework, what you would do is you have some classical data, and then you would have some function or some model, which is a function of x and theta. Even classical machine learning, you have some parameters, you have some cost function, and then you update these parameters theta. Right? Now, what you are trying to do here in quantum machine learning, you're just replacing this model, this classical model, with a variational algorithm. So for example, we are talking about the variational quantum classifier here, right? No, now here what is your input? So you'll of course design a quantum circuit wherein your input is your labeled training data, your output is your predicted labels, and these steps are something that we spoke about. So you have a classical data to quantum states, you apply an ansatz, you measure the circuit, and then you optimize. Right now we spoke about multiple that there are multiple ways you can encode the classical data into quantum states. So I just wanted to spend say 5 minutes on a couple of encoding schemes that would be very useful for your hackathon implementation as well. So the first one is called basis encoding. So as the word suggests, what you're trying to do is you're trying to encode your classical data into your computational basis state, right? So suppose you have a data which is x, and this has two data points x1 and x2. So what you do is you first encode this in terms of binary. So you say this is 0 1 and this is 1 1 1. So now if you have two qubits, so you can actually have these kind of states, and you say that okay, this is going to stay in 0, this is going to stay in 0 likelihood, and these two states are going to be your input data. So x1 is encoded as 0 1 and x2 is encoded as 1 1, right? Now this is value approximation by their binary representation. The advantage is that these are very good for arithmetic operation. However, they're not efficient in terms of number of qubits, right? So as many data points you have in your say data, you will need that many number of qubits. So you are actually using a lot of qubits in this encoding scheme. So we are so with that disadvantage, we are motivated to look at some encoding schemes which would give you some advantage in terms of minimizing the number of qubit usage, right? So let us consider this is your circuit. You have these Ket0 states, and this is your quantum circuit, and then you take some outputs. And what happens typically is you have a tensor product, right? So you just do a Ket0 tensor Ket1, and yeah. So what is this? You can just break it down. So you can write this in matrix notation as 1 0. This you can write as 1 0. And if you do this, this will become a 1 over 1 0 and 0 over 1 0. So this means a 1 0 0 0. So now you see the size of this. This is actually 4. So you started with two qubits, and you had 2 to the power 2 states, right? So if you say that there are n qubits, you can actually have a 2 to the power n states. So or the reverse you can say, and I'll just ignore the math here. So if you have n qubits, you are able to now encode 2 to the power n features. Or the reverse is when you have a data set of 2 to the power n features, you can do it with just n qubits. So a logarithm reduction you are being able to do here. For example, if your classification data has say 8 features, okay, 8 features could be height, width, mass, weight, and whatever is your features. So you will not require 8 qubits anymore. You can just work it with 3 qubits. So there's a drastic reduction in qubit, and this 8 to 3 doesn't sound like really drastic, but imagine if you had a 2 to the power n features, you are now just requiring n qubits. So you can actually do a qubit wise kind of an encoding scheme. Now the third encoding scheme is an angle encoding. So if you have some angle, so if you have this data set which is x1 and x2 are 2 data points, you can actually say that okay, I encode x1 as the rotation, as the amount of rotation that I want to put. So this angle is represented here in the amount of rotation. It could be rx or ry. So basically it's rotation over x-axis, rotation over y-axis, or rotation over z-axis. But what is that amount of rotation that you want? That is your data point. So you encode your data points as rotation or as angles. So that's called angle encoding. And then there is a higher order encoding as well. So just think of angle encoding, but we are doing a couple of steps more here. So first we are putting these qubits in superposition. Then we are doing some angle encoding. Then we are entangling it. And then we are doing another rotation, which is now this is the encoding which is depending on the product of these two features. So x1 and x2 were your two features. Now you're doing an x1 into x2 and you're encoding with that. That's the reason why it is called higher order encoding. And there is a lot of theoretical work which says that this higher order encoding is better or can give you better results for different sort of problems. Now this entanglement that you see here, I have sort of drawn a linear kind of a entanglement. It could be any entanglement. It could be linear, circular, full, anything. And that gives you the liberty to create different types of higher order encoding. So different types of rotation axis, different types, and even different repetitions. So you can repeat this entire feature map multiple times. And there are some theoretical some papers wherein they talk about okay, if you increase increase the depth of feature maps, it is generally going to be better. So you will have a increased or a better kind of results, right? Now, yeah, maybe we'll skip these, and yeah, this is a lot actually. So we'll skip this, and we'll actually talk about a problem. And okay, so we had these steps, right? So we were having the answers, we were measuring it, and we were optimizing it. So in terms of the optimization part, you can actually do similar things like you have in classical machine learning, which is more of, gradient based learners. So you can do a gradient based learning, you can also do a non-gradient based learning. So just to show how would you compute gradients here, there's something called parameter shift rule, which you might have heard of. So I take my theta and I take a value of theta plus s, I take a value of theta minus s, and I compute this entire thing, and then I measure it, and then I compute the difference, and it's going to give me, okay, what is that amount of shift and how is that shift impacting, right? So I'll get different values of theta at different t times, right? So you can use different sort of algorithms like adaptive gradient or ADAM algorithm, which is used classically as well. Then there are other classical optimizers, for example, Kobaila and SPSA, but we don't have the time to go into details of Kobaila and SPSA. I'm just giving you that these are the things that you can use in a variational quantum circuit, and why it is known as hybrid is also something that we wanted to look, right? So there are some parts of it that run on a quantum hardware and some parts of it that run on a classical hardware. Okay, so now let me try to see if I can cover a bit. I'm taking some time from your lab, but I hope that this is going to help. So cover the theory of both the algorithms. At least we should learn something very well. Now we're coming down to the second algorithm, which was your kernel SVMs or quantum SVMs. And okay, there's a question. Maybe I can take up a question. Can Devashmita, Ritajit, can you read out the question, because I can't see the...
So the last question I can see is ADAM optimizer we are familiar with, but what is Kobaila?
Okay. So Kobaila is another kind of a classical. So these are all classical optimization schemes. Okay, Kobaila or SPSA. So all of these are classical optimization schemes, and these are both of these are non-gradient based optimization. So what happens in Kobaila is it's an iterative approximation algorithm, and you keep approximating using some linear programming tricks, and when the solution, you don't get the solution, you sort of minimize or decrease your step size. So you keep decreasing your step size, and you're trying to come down to this global minima, and then even if after a certain point you are not being able to reach there, what you can do is I mean when your step size has become very small and you're still not making any the loss curve is not going down any further, that's the time when you say that okay, the optimization is complete, right? And in SPSA, how SPSA works is SPSA, I can't go to the entire theoretical. So simultaneous perturbation stochastic approximation it is called, because it is another approximation algorithm, so it's not computing the gradients at all. SPSA is typically useful in two cases. Okay, so first thing is problems where the gradient estimation is very hard, or it is taking huge amount of time, right? So those are places where you want to use optimizers like SPSA. So it can approximate the gradient using these quantum circuits. The second thing is it is often preferred for these hardware kind of experiments, because quantum gradients on hardware have some noise, right? And SPSA is robust to some sort of noise or some sort of error. So that's another reason why for hardware runs typically people prefer SPSA. Okay. Any other questions, Devashmita?
One more question is, can meta heuristics be used in quantum circuits as optimizers?
What do you mean by meta heuristics?
Okay, and there is
Okay.
one more question, that how you are using RBF in quantum kernels.
Well, that we can easily use. So RBF is just a kernel function, so it's basically a Gaussian kernel function, and the Gaussian kernel function is something very easy to do classically. Okay, so you can, it's easy to do both in classical or in quantum states. So you can implement the same. It's the same equation, same formulation, and you have these inner products of these feature maps. So if once you have these inner products of these feature maps, you map it down to a Gaussian function. That's the only thing that you do. Okay. Okay, so maybe are there more questions, or can I cover a bit of these kernel SVM theory
We can
and
take
then
the
maybe?
questions later.
Yeah, then we can before lab maybe. So just give me say 10 minutes and we'll cover this portion as well. Okay. So yeah. You guys can see this, right? Okay, so I'm just trying to motivate something here. So let's say that you have a set of data points which is x1 to xm, and each of these on each of these data points you have a kernel. So this is your kernel, and this is represented as k of x bar x. This is your new data point. So given any new data point, you're trying to match, say, distance or say some similarity with this particular data point, which is x1, right? And maybe I should remove these annotations here. And then what you can do is you are sort of anchoring each of these data points with some kernels. And then if you can actually create something like a probability density function if you sum it across all these kernels, and then you'll of course get a larger width kind of a probability density function. So what is a probability density function? From which you have sampled out these probabilities of each of these data points or kernels, right? Now, quantum kernel density estimation is an algorithm which is typically saying that, okay, given a probability density function that I have, can I now sample it and get these values? And we are trying to now use this algorithm of kernel density estimation, and we are saying that we are going to convert this algorithm as a classification problem. Okay, now let me try to give you guys an overview of this. So here in two different colors we have two different set of data. So one is, where's my pen? Yeah, so one is a set of data points x1, x2 and say to xm, and then you have another set of data points which is alpha 2 to alpha m. Okay, now you come up with a new data input which is say beta. Okay, and then what you do is you are now trying to say that, okay, we'll compute some kernel or some density or some distance, and then we are going to find out whether it is falling into this red class or whether it is falling into this black class, right? So mathematically what does that imply? So it is just saying that, okay, what is the first step that you did? You had these individual kernels, you summed it up to create this larger kernel, or in that kernel density estimation step. So first step that we are going to do is sum over all these data points this kernel. So k of x of m comma x, this new data point x, here we denoted it as beta, so it should be beta. And this summed over this is what your initial thing is. Then you are saying is I'm weighing it with the class label. So these are weighed over this class label, so that's the reason they are grounded, right? So then you have to multiply this, which is y of m. So this is the label of each data point, where y is your label, and you're saying I am multiplying each of these with the label of each data point, and then I'm just thresholding it or just scaling it down. So I'm saying that, okay, this is some sort of a squashing function, wherein if the value of this is say greater than 10, then it belongs to class 1, and if it is less than 10, it belongs to -1, just to give you an example. Okay, so this is sort of the function, or this is sort of the formulation that you saw in SVM as well, right? Now I need to shrink this significantly. Okay, so now we can think about a kernelized classifier, and I'm just giving you the intuition here. So let's say we have a data set of 4 points, and then you can actually write it like this. So there are these values of the data set, and say you have some kind of way to compute this, right? So you know k of x1 to x is 5, so you have the distances. Say this is a distance kernel, and you have the values. So this is 5, this is 2, this is 0.1, this is 0.1. So this boils down to this function. You can write it as minus 6.8, right? So this minus sign sort of decides which class it belongs to. So now this belongs to a -1 class. Had it been a plus thing, then it would have belonged to the +1 class, right? And this amount is saying that, okay, how much it is towards the negative direction or towards the positive direction. But the sign is important, and it's a deciding factor, or it decides at which class you can fall it back. So this is sort of a binary classification problem, right? And in this kernel SVM, that's what we were trying to do. We had the primal and dual formulation, the equations that I showed you, and in that equation you had a small k first brackets x of m x. Here what are we doing? We are just replacing in these two equations something in this red, which is a kernel, or which is an inner product of two kernels, right? So this replacing thing is the kernel trick thing. Okay, and we'll not go into more math in the interest of time, but there are some properties that these kernels should possess. But we'll look at some of these actual notebooks to be able to understand how each of these things work. Shift this to this. Okay. Again, maybe this is also too large. Is this not become? Okay. This looks okay, or is it still too large for you guys?
Yes, this is fine.
This is fine. Okay. Okay, so so I'm running over 5 minutes, but I'll try to cover that. So we'll go over a couple of notebooks to be able to see how we can use variational quantum classifier and quantum SVM. So each of these topics actually take multiple class to cover the theory of it. And what was coming next in my notes that many of you might have seen is all the math and all the proof. So how can you say which is a valid kernel? So it should satisfy those properties. How can you describe it in, how can you solve the primal dual problems? So all those derivations is what is important to be able to fully understand the potential of a QSVM. And then one more thing that I'll just tell, I'll not show or explain, which is there are a set of kernels that are known to give some advantage. Okay, so for example, theoretically there's a problem, or there's a class of problem in computer science which is called the one-way function. So for example, x plus y equal to z, and x plus y is doing very easy, but from z getting x and y is hard. So plus really doesn't sound or make it that hard. So for example, think of coffee, right? So you have milk and you have coffee powder and you have sugar. So you combine these three. So if I tell you that, okay, you have to take this many quantity of each of the thing and combine and create the coffee, you know it, right? It's an easy problem to do. Now if I give you a cup of coffee and say, estimate how much coffee powder is in this, that's a very hard problem to do, right? So these are sort of one-way functions, and typically one-way functions are used in cryptography and for data security and security problems, because so one side you can do it, but the reverse no one can do. So you can encode your passwords in that way that an adversary can never get your password or can never break that security, right? So there is one such function which is called discrete logarithm function. So discrete logarithm function is one function that has been used as a quantum kernel, and it is something very hard to compute classically. Also, what it showed is if we have a good choice of fiducial state or initial state, so if we have a good choice of initial state, it makes the classification problem very easy. Okay, I can't go into all that detail today, but it's just to show, just to give you an idea of there are these quantum kernels, and you can use quantum circuits or unitary circuits which are very hard to compute classically as quantum kernels, and that would potentially be a way to get quantum advantage over real world problems. So those are kind of the kernels that we say, these are the quantum kernels in practice, right? And if you want to learn more about it, so the Quantum Global Summer School 2021 had a lecture, I think lecture 7.1 to the best of my memory is the lecture on covariant kernels, and you can understand about the kernels and which kernels can give you some potential advantage. Okay, so you all might have access to Quantum Lab or Qiskit, and here if you see there is this kind of if you go here, you'll see here. So if you go to lab files, Qiskit tutorials, there's something called Qiskit machine learning, and you have a lot of notebooks that are available on different algorithms. And today we are not going to cover a lot of algorithms, although I thought of covering the first one. That's the neural networks. And since we have covered variational quantum algorithm, classifier, and QSBM, I will try to cover these two notebooks for today. Okay, so there are different ways that you can use this neural network classifier and neural network regressor, or you can implement VQC. And what we are going to do is we are going to look at VQC using opflow QNN and VQC using circuit QNN. Okay, and what are each of these? We are going to talk about all of that. Okay, so there are a couple of import statements which I'll not go through in detail, but from Qiskit we definitely want to take quantum circuit. We are taking air here, and if you want to run it on a real hardware, you'll also have to take IBM Q. And then of course from opflow you're taking a couple of these things, and we are going to talk about each of these in detail in the subsequent cells. And here you're taking something called a ZZ feature map. Okay, so ZZ feature map is one form of a angle encoding scheme wherein you have some rotation. We went through angle encoding schemes for that reason. So you have your data points. You encode your data points as angles to rotation gates, and then once you have the rotation gates, if you just stop at that, that is called a Z feature map or a poly Z feature map. And then if you have a second order poly transformation, which is your ZZ feature map, what you have there is an entanglement even after the rotation. Okay, so in most of the Qiskit notebooks, you'll actually see usage of ZZ feature map, and that is primarily because ZZ feature map has this ability to bring in entanglement. So you're bringing entanglement in your in your data encoding scheme. Okay. And then, of course, there are some things from Qiskit machine learning algorithms. You're directly getting VQC, you're getting two-layer QNN. This is a way you can create your ansatz, and you can also use circuit QNN to create your ansatz. And this is the particular class that is a very self-sufficient class, and you can just use this class VQC. If you don't want to go to understand the detail of how VQC is working, but you have a data, you want to just try out VQC, you can just rely on this particular class. So here is a simple classification problem, and there is a simple data set. So they are now first step is they're preparing a simple data set and they're trying to plot it. So if you see, this is a two-class problem. It's some blue balls and some green balls, and there are some data points that might give us a hard time classifying them, because there's one point which is here, there's one point here, there are these 2 points that are quite close, or this point that is quite close. It's a mix of things, and in between you can actually try to draw a plane and have a linear separation, right? So we'll not go into what is opflow QNN. If you want to read that, just focus on the first notebook of Qiskit machine learning, and that clearly explains both opflow QNN and circuit QNN. But let's consider this as black box and just try to understand VQC for today. So here you're saying that, okay, you have two classes, +1 and -1, and you're using a couple of functions, which is offlow QNN and two-layer QNN, wherein you have the feature map defined and an ansatz is predefined. Okay. And so this actually if you give what is the number of inputs and which quantum instance or which quantum backend do you want to work around, it is going to create the circuit by its own. Right, and you can create these parameterized quantum circuits yourself as well without using these Qiskit functions. Okay, I'm just calling it out. Now after that we have a callback graph. So we want to draw the loss landscape. So how with every iteration the loss is decreasing, and that's the reason we have this callback. So callback is going to give you after every iteration what is the value of loss. Okay, if you don't want the value of loss at every iteration and you don't care about the intermediate steps and you want to look at just the final results, you don't need the callback graph. But I would ideally suggest that have it, because that gives you a very good control on how is your training happening. Is it overfitting? Is it underfitting? Is it still lot to go? How can you decide how many optimization steps you need? If you look at your loss function and you see it's still staggering somewhere, then you may need way more number. But if you see a flattening is happening, then you would like to decrease the number of iteration steps and include some regularization parameters, for example, things like early stopping and stop the training right off. Okay. And then now here they're calling this neural network classifier. This classifier, this particular class is explained in the first notebook, wherein you pass it, okay, what is the type of QNN or what is the type of ansatz that you wish to do, and which is the optimizer. So this is the Kobaila optimizer that someone just asked, right? A constraint binary, constraint optimization by linear approximation. So this is Kobaila, and of course you're saying that I want a callback, right? Now here, so you create this sort of a function, and you now say that, okay, train it. So training is again very simple. So you're using a lot of things from scikit-learn. So you're just saying dot fit is your classifier, dot fit is your classifier, dot train, and then dot score is your testing mechanism. So you pass the data. So you pass the x and the y. X is your input features and y is your label. Again, you pass an x and y. So you're just training and testing on the same data point. And here you see that this is sort of the loss function. This is the advantage of getting that callback graph. So you see that, okay, starting it was randomly decreasing, and then at a certain point you're seeing it's still decreasing. There are jitters, but it's sort of stagnating, and you get an accuracy also. So you get a score. So you get a score of 0.8. Right. So you can use this the same way. And now what you're trying to do, you're trying to evaluate your data points. So you're trying to say that, okay, which data points performed, and this is still on the training data. So in the same data, you're just saying that, okay, which data points did well and which data points didn't do well. And you see that, okay, these are the problematic points. So the points circled with red, and okay, there's some question for admin. Okay, and we see that there are some particular points which are sort of problematic or erroneous or wrongly classified. Right now, then there is a classification using, so you can do both of these classes. So you can either, so here we created this with a 2-layer QNN. So this 2-layer QNN is actually combines both the feature map and the ansatz. You can do the same thing using something called a opflow NN, and here you're just calling an opflow classifier, and you're asking that, okay, with an opflow, here you're calling a circuit QNN, and with circuit QNN, how can we do the same? So the steps remain the same as that I showed you in the slide. So first step, you have to construct a feature map. Here we are using ZZ feature maps. So we are taking our classical data using ZZ feature map to load it into quantum states, and then we are constructing our ansatz. Here there is a function which is called real amplitudes. You're using real amplitude. You can use something else. You can use something called toLocal. toLocal also creates helps you create ansatz, or you can define your own ansatz as well. So you can have a separate cell on top and define your own ansatz wherein you want a certain amount of rotations or certain amount of things. Now in machine learning, we see that these kind of ansatz preparation is generally very heuristic based. So there is no such motivating thing that, okay, this particular ansatz is definitely going to work well for all problems, right? Or it's very problem specific and it's very heuristic based. Versus in problems like chemistry, what we have is we have some domain inspired ansatz, right? Wherein you know that, okay, the molecules move like this. So there is a particular Hamiltonian which sort of indicates what is the potential energy or what is the kinetic energy. And if I can create an ansatz which is sort of a good representation of that Hamiltonian, I'm likely to be able to do better. Okay, so that's one thing. And then you have this, so if we just go back to our slide and recollect the slide, so we had first point was the data encoding, second point was ansatz creation, and third point was ansatz, we want to run this ansatz. So I've just tried to draw it, so just to give you guys an intuition of how it looks. So you have your ZZ feature map, and you can even decompose and draw each part of it, and then you have this is the real amplitude. So this is another function that you used. And then once you have this, you can have some measurements and you can do some post processing. Here they are doing parity post processing. So just to give you guys an intuition of parity, so suppose you have these 4 states. So it's a 2-qubit circuit here, right? So you'll have 4 states 0, 0, 0, 1, 1, 0, 1, 1. And let's say you say that, okay, even parity belongs to one class, odd parity belongs to one class, right? So you can actually pose it as a classification problem using parity post processing. That's what you are trying to do here in this parity function. And then you say that, okay, now I know that I have constructed my circuit QNN has this particular QC circuit, which is here. This is your QC circuit. Then you say that, okay, I have my feature map, which is your ZZ feature map. I have your ansatz parameters. I am saying that you have to interpret the measurement probabilities using parity, and then you're passing a quantum instance. Quantum instance is generally the backend that you want to run. So you might want it to run in on some simulator or on some hardware, which is something that you choose, right? And then you are just constructing this classifier using this class. So you don't have to do anything. This class is automatically constructing your classifier. But I would strongly recommend, if folks are interested in this, go back to this class, and the entire code is available in Qiskit. You can actually understand how it is creating the classifier. Okay, and that is something that we covered in a very brief and fast way in the math part. So it would be interesting to see in the code side how do they do. Okay, so then the same steps remain here. So we are just trying to do a fit with a given data point. So the data point x1 and a label, and on that same data point we are trying to say that, okay, score my model and show me how it performs, and this is typically the loss curve for that. Okay, and then you want to predict it and say that, okay, which are the ones that are again running bad, and these are the ones. So we had actually expected that these guys are going to do bad. However, this is surprisingly not doing bad, which is like, it's a synthetic data generation, so somehow it is not doing, it's doing a fair bit of job with that particular data point. So variational quantum classifier is a special variant of the above two classes that we looked at, and here you will be able to even clearly see the same steps. So you have the feature maps, you have the ansatz, you construct the VQC, you're just using this VQC class. So if you don't wish to learn about anything till this part of the code, that's fine. All you need to implement a VQC is just these two cells. So you have a VQC class, you pass the feature map, ansatz, you pass what is the type of loss function, you can define your own loss functions as well, and you pass what is the name of the optimizer that you wish to do. Here you can also give something like, max iteration equal to say 100, 200, whatever number of iterations within this algorithm that you wish to do, right? And then again you will see that, okay, how is it training? Is the training getting any better? How is it testing? So the testing is just VQC predict, and you pass the data points which you want to predict. Here you see you're not passing it the Y. So if you don't pass the Y, it will not be able to give you the classification report or classification matrix, but you can still do a prediction. So this is for a random test input where you don't know the Y, and let's see where it belongs to, and you can see that. The same thing we can do with a variational quantum regressor as well. I'm not going into the regression details, but you can do a variational quantum classifier. You can also do a variational quantum regressor. The only difference is, instead of these discrete points in a classification setting, now you have a continuous variable that you wish to predict. It could be say height of kids in a class, or age of trees from their rings, or something like that. Okay, so those kind of things also you can see. So you can go through the rest of the code to understand how they do regression. Okay, so now we're going to look at a quantum kernel implementation. So any questions pertaining to VQC, it's a good time to take now.
Shomodi previously asked that can meta-heuristics be used in quantum circuits as optimizers? Later he explained that by meta-heuristics he meant the genetic algorithms, etc.
Yes, so okay, so genetic algorithms are used for optimal ansatz selection. That is one place that they are used. For ansatz selection, there is a vast range of things that people use. But and this entire space of ansatz is heuristics. Okay, so you can say that there are multiple things that are very heuristic based, and people keep trying. Okay, so that's something that is common. So I'm not sure about what all you mean by meta heuristics, but all of these ansatz selection is heuristic based. So you can use any sort of algorithm to be able to do better in terms of a choice of better ansatz. There are some papers which say that, okay, what are the ansatz specific properties? Okay, so just stop sharing and reshare from this screen. So yeah, this screen should have a good font rendering, and I should be able to see chats here. Yeah. So what happens here is, for ansatz selection, there are different algorithms and there are different metrics also, which sort of indicators of ansatz quality. For example, there was a paper which talked about expressibility and entangling capacity. So we say that, okay, entanglement is something which is very core to quantum algorithms. So then entangling capacity of a circuit should ideally be a measure, right? And is it that more entangling capacity is better for my problem? Often not. Or less entangling capacity is better. So it is very problem dependent, and given your application, you can find out, okay, how much entangling capacity do I really need to be able to do a good job in, say, getting a higher accuracy. Same for expressibility. Expressibility means that what is the capacity of this parameterized quantum circuit or this ansatz to cover the entire Hilbert space, right? So is it being able to cover the entire Hilbert space? That would be a highly expressible circuit, versus if the circuit is limited to some, say, some part of the Hilbert space, then we'll say that, okay, it's a, it's less expressible. Right, so these are often used as metrics, and in order to say that, okay, whether this is a expressible ansatz, non-expressible ansatz, more entangling capacity, less entangling capacity. Even people do, for hardware runs, people also focus on circuit depth and circuit cost. So circuit cost basically is things like how many rotation gates you have, how many 2-qubit gates you have, how much entanglement you have, what is your circuit depth. So sort of a function taking all these parameters is called your circuit cost. So that's an interesting paper. It's from Alan Espiroguzic's group. I think a 2019 paper that you can also see if you're interested in that space. Okay, so with that, this becomes now too small. I'll try to increase it a bit. And oh, there's some latency. Can I cite the paper? Yes. The paper is called Expressibility and Entangling Capacity of Parameterized Quantum Circuit. Most likely that's the paper. You can just search it with this title and say Alan Asperoguzik. Okay, so it's a 2019 paper. So that paper covers it all. Okay, so now we'll come to the second notebook, which is quantum kernel machine learning. And here, so this is actually the third notebook in your Qiskit machine learning tutorials. And most of the theory, I mean, we covered very brief theory, but some theory of it is also given here in this particular, notebook, and you can go through that. So here, what are we trying to say? We are saying that, these data points can be understood better when we can project it to some higher dimensional space, right? So there is a kernel function K of xi xj, which is basically some inner product of f of xi and f of xj. Right, so these two f, I mean this f is a feature map. Don't confuse it with encoding schemes, right? It's a feature map, and what is a good part of it? I don't really need to know how to compute this feature map and how to get f of xi. I don't need that value, explicit value. If I can compute the inner product of f of xi and f of xj, I'm good. Okay, so I don't need to fill every value in this kernel matrix. If I know the inner product, I'm fine. Right, so that's what we are trying to look at here. And here, one more thing that we saw, I mentioned when we were going through my handwritten notes, is that if I can compute this kernel, right, I can do the rest of that in a classical optimizer, or I can even use classical SVM. So that's what we are going to do in this tutorial. We are going to use classical SVC, and many of you might have used it. So this is support vector classifier, and this we are going to use from sklearn. So sklearn has a class SVM. From that we are going to import this, and this is a classical support vector machine. Okay, so we are just going to do our quantum part, and that for that we are importing this class QSVC, and we are going to import something called a quantum kernel. So we are going to do the quantum kernel part in a quantum hardware, bring it back and do the optimization in a classical hardware, and this classical and quantum hardware are going to constantly talk till they minimize to some common decision. So we'll take a classification example again here, and let's first try to get a data. So Qiskit actually has a data called ad hoc data. So here from Qiskit machine learning datasets, you can import this data called ad hoc data. And so they're just importing this data. They're taking some 20 for training, and they're taking some 5 data points for testing, and they're trying to plot it. And eventual result of this plot is like this. So wherein you have these hollow ones for train, and the solid ones are for test. So you can sorry, the hollow the hollow ones are for train and the solid ones are for test. And these red ones is one class, and the blue one is the class A. And once this is plotted, you see that this is a problem which is definitely not linearly separable, right? It's everywhere. So you can't really draw a line like this, right? You can't really go over like a typical curve fitting, and you can, I mean, you're bound to overfit if you try to do a polynomial curve fitting on this problem, right? So what is a good way to do? Imagine that you have this in this plane, and you have some way of, you know, rotating this plane, and then you see, okay, all the blues emerge here and all the reds image here. Or you can actually transform it to some higher dimension, where you see that the blues are left behind and the red came up with you. Okay, so that's what you do in your in this as the very first step, right? So you try to put it to some higher features, higher dimensions. Now, what were the points in a variational algorithm or in a quantum classifier? In our slide, we saw that the first step remains still that, okay, you have a classical data set, so you have to put it into these quantum states. So you have to use some feature map. And as I mentioned in the previous notebook, that, you know, Qiskit, in most notebooks of Qiskit, you will actually see ZZ feature map. And the reason is that you have a way of entanglement within the feature map. So it's considered a harder feature map to do classically. And that's the reason it is more prevalently used here. So you can use ZZ feature map or some other feature maps as well. And then they are also saying that, okay, give me 2 repetitions of ZZ feature map. It's not just ZZ feature map, but it's applied twice. And the type of entanglement that you are keeping in the feature map is linear. And what is the feature dimension? The feature dimension in here is the same. So because you're encoding the values, if you remember, we had x equal to x1, x2, and you were saying that, okay, rx of x1 and rx of x2. So you are encoding each value or each data or each feature as an angle in here for rotating the qubit. So you will have as many number of features and that many number of qubits you will have to use. So your feature dimension is your ad hoc dimension, which is 2 in this case. And you then choose a backend, which is here they've chosen a custom simulator. You feel free to choose any simulator or actual hardware, and of course do make the runs on hardware that is going to give you a realistic understanding of the hardware, and you know where your simulator is showing you and how far your hardware is in that journey to come close to that noise-free results. So here they are now taking this quantum kernel, and they are saying that, okay, given this feature map, so you have this ad hoc feature map, you take this feature map and you take this quantum instance, which is whatever device you have chosen, that will that you pass these 2 into your quantum kernel and let your quantum kernel do the job. Again, you know, I'll suggest you guys to look at this particular class quantum kernel, then you will be able to understand all the, you know, handwritten notes that we were going through in the class today. So now the next steps are pretty much similar, and you can actually use a classical SBC, right? So once you have built the quantum kernel in your quantum hardware, we just
Anupama, is it possible to just zoom this a bit?
oh yes. See. Is this any better?
Yes,
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 this is
yes.
Yeah. Okay, great. So the steps where we had a feature map, we had a backend, we created our quantum kernel, and the rest we can do classically. So we just call scikit-learn's SBC, and then we pass the kernel here. We pass this ad hoc kernel, okay, which is the quantum kernel. So this is the only change. Note this line. So had you had to do a Gaussian kernel, a simple Gaussian kernel, you would have defined a Gaussian kernel, or you would have in single quotes the way we write RBF, and you can call this, you can have this passed in this kernel, versus what you are doing here is you're creating some quantum kernels in your quantum hardware, which ideally should be something which is hard to generate classically. That is the function that you are putting. For example, I was talking about D-log kernel. You can have a D-log kernel here, or you can have any other kernel here. And then what you do is you can have your ad hoc SBC fit. So you pass your training data and your training labels, you train your model here, and then you have your ad hoc SBC score, which is on your test features and test labels. And then okay, so this was a synthetic data set, and you are doing a fantastic job, of course, on a synthetic data set. And this is a very small data set. You just have 20 data points in train and 5 data points in test, so you're naturally going to do very well. And this is an interest of showing in a tutorial, but you can work on real world problems where you'll start seeing the hurdles of classification. And if there is a problem that is already struggling in terms of classical SVM, that is a very good problem to actually apply quantum SVM. Okay. Now, so what we can do here is a couple of things. So in this part we are trying to see, okay, how, I mean we see a classification accuracy of 1, right? But we want to still go back and in your case, if suppose you are getting a classification test score of 0.8, so you want to see what went wrong. So you want to know what are the kernel matrices, how do they look, and this particular code snippet is just trying to give you the training matrix and the testing matrix. So this blue is your training matrix, and this red is your testing matrix, and you see there are 4 quadrants that are neatly emerging, and this diagonal is the darkest, which is a good news for us, and that's the reason you see a 1 here. So diagonal elements is, it has to be predicted an I, and it is predicted an I, so it's the correct prediction. So diagonal elements are definitely, you're getting it, but you are still getting some other values in some places, right? So that's something that is happening here, although this is a very ideal distribution to get. Okay. Now you can do some extra things also, and in this notebook they are actually going ahead and talking about things like clustering and all, but because I didn't cover classical clustering or quantum clustering, so I'm not going to go to that part of the code, but you guys can look at that part. There are quantum algorithms in the clustering space as well, for example QBoost and QK-means and all, and if you are interested, you can go into that space. But what I will focus on in the rest half an hour is, now you have a way of training and testing these kernels, right? Now can we do more on it, right? For example, in machine learning, in deep learning, you have this concept of pre-trained models. So you have large amount of data, and then you have these kind of models which are, for example, the BERT models or the transformer models, and then you learn on these large data, and then these learned model you want to load, and then you want to, so if your particular data set is a small data set, right? But if you start training such a large neural network, so over parameterized neural network, if you train on a small data set, it's going to remain underfitting. I mean, it's going to have a severe underfitting, right? So or it might overfit and the results might be very bad. So you are seeing that, okay, you're not being able to do a fair job in training, but if you load this pre-trained model that has already seen the world, right, has already seen significant amount of data, it can use its experience and learn better on your domain, although in your domain you had a small amount of training data. So this is called something like a warm start from a pre-trained model. And we'll see how can we do that in quantum. Can we do that in quantum? It will be hugely beneficial, because we are saying that quantum hardware is not being able to take in huge amount of data. So if I train a model today, and with some good luck that I had, or with some priority queues that I had, I am being able to train a model with, say, some hundreds and hundreds of data set. But I had this model loaded and saved. Now when I have in the next day, when I have to run it on some other data, I've generated the data and I want to train the model, rather than training from scratch on the cumulative of both the data or on only this data, I can warm start from this saved model and learn the rest. So that's what we are going to see in this particular code. Okay. So any questions so far?
Yes, so there is a question by Shomodeep. He is asking that in ML, we have a characterization of the power of hypothesis space in terms of VC dimension. Is there
Yes.
a similar quantification in case of quantum classifiers?
Yes, we do a similar thing in terms of bias variance as well. Actually, I should have shown this. I don't know if this is there in this particular code. No, I don't think so. So actually you can do a similar thing in most of these. There are mechanisms to do that and have a concept. There are also, but they are mostly in these research stage. They're in research paper state, and there are several concepts which could be I can't say equivalent, but they could be analogous to VC dimension. Okay, so there are different tricks in quantum machine learning. We would rather say, because they are, some are researchy, some are very hypothesis based, wherein you have, say that, okay, I can say that this model is trained well or this model is not trained well, with something which is not exactly VC dimension but close to that. So there are different papers there, and there is some amount of work that is there. I mean, and one reason that probably that is not very interesting is, um, that does not give any advantage in terms of the model understanding. I'm sorry. That does not give any advantage in terms of the model understanding. Okay, so that's probably one reason why we don't see a lot of papers in that direction. So yeah, I was just
Also,
trying to.
Soumodip previously asked that can you like suggest some notes or something from where he and others can also study these things.
Yes, yes. So yeah, there are plenty of sources, but Qiskit, I mean, sorry, for quantum machine learning, there's no such proper textbook. Okay, so Maria has a textbook. So Maria Schuld and Francois Petronoche. So they are the authors of this book, but this book is on supervised quantum machine learning. It is I mean, it covers a good amount of things in that paper as well, but because this field is very nascent, right? It's growing at a very fast speed. So a better resource is Qiskit textbook or Qiskit machine learning tutorial, which are constantly growing. So Maria's book is a good starting point if you guys want to, but I would rather say Qiskit textbook or Qiskit machine learning because it's constantly getting. So every paper that we publish, or anyone, not just IBMers or anyone in the outside the Qiskit community, or in the Qiskit community, but outside of IBM, whenever we publish a quantum machine learning paper, we make sure that we put it back in either the Qiskit textbook or in Qiskit community tutorials or in Qiskit machine learning library or Qiskit machine learning tutorials. So this is something which is constantly getting appended and growing with time, versus the textbook didn't. So there was another textbook by Peter Wittek. I don't know if you guys know Peter. So Peter actually would have been a very good person for quantum machine learning. He has a course. In 2019, he actually was planning this course, and you can just search quantum machine learning Peter Wittek on YouTube and you'll get the videos. It's, I think, close to 40 lectures. Each lecture is like some 5 minutes lectures. It's very good. It's very crisp. Whatever he could have recorded, that is uploaded on YouTube. It was in, I think, some MOOC course that he was planning, but unfortunately he was visiting that same month, September, he was visiting India. He was somewhere in Uttarakhand and there was an avalanche, and we never could find him back. He had a book, but that book has now become very dated, and maybe very soon Maria's book will also be dated. So I can't suggest a textbook, and I would rather say that research papers are where, I mean, because it's a nascent field, right? So you'll have maximum things in these nature papers. So an easy way to follow is just search quantum machine learning in archive, and you'll have a list of all the quantum machine learning papers. So every paper first goes to archive or goes to some journal, and till the time it is published, it is hosted in archive. So you can actually look through that as well. I'm not giving short answers to any questions today. I don't know why, but okay. So yeah, let me, somehow my screen sharing stopped. Okay, so I'm just trying to search something. Let me see if yes. So this is one demo that I normally did. Maybe I can go over this. So if you have some, so let's look at a demo code first, and then we'll look at the warm start problem. Okay, so this is a VQC demo. So you have these import statements, and I have access to some providers. So I've listed these providers, and these are open access. So you all should have access to the same providers. And there is a way that you can actually see what is the least busy. So if you just, so I'll just uncomment this, and then you can actually find what is the least busy machine. Here what you need to do is, suppose whatever is your qubit, number of qubit requirement, you can say 227 or whatever it is, and you can say that okay, the device needs to be in an operational state, it shouldn't go to under maintenance, and it should not be a simulator. So that kind of a device, please give me back a device like that. And of course, then you have these import statements you saw in this second notebook, or the first notebook that we did. So, and here of course I'm running it on a state vector simulator just to show you. This is the same ad hoc data set. So you saw the data, I've just plotted it in a simpler way rather than having that complex red blue plots. So we see that okay, even here we can see it's not linearly separable. I've also printed the actual data points. You can do all of that. And then I take a ZZ feature map, to local, VQC it, train it, test it. We can print the training time, testing time, decompose and draw the answers and do all of that. And after that, what we can do is we can print the classification report similar to that what you do. So this classification report, this is a function from scikit-learn. This confusion matrix is a function from scikit-learn. This has nothing to do with quantum. So once you have this model trained, you can actually do all of these on top of it. Just to understand, so for class 0, how is it performing in terms of precision recall, F-score, how for class 1, how is it performing? You can get micro average, macro average, weighted average and everything. So you can get all these details. You can also get accuracy and so on. You can also get the confusion matrix. So this is the number of true positives. So positive, positive. So it was actually positive, classified positive, versus actually positive, classified negative, or actually negative, classified positive. So this is a false positive and this is a true negative. So actually negative and true negative. Right, so you can get this confusion matrix and all of this also you can get from here, right? And this is different ways of creating different answers. So we showed you one way. This is another way by using toLocal. So I'm saying that okay, toLocal, get me 4 qubits and then do some kind of an answers, which the answers looks like this. So there's a rotation over x-axis, there's a rotation over z-axis, there's some entanglement, which is some here I'm using a cx or a c0. You can also have different types of entangling gates like a cz or something, whatever is your requirement. And what is the type of entanglement? So you can have a linear entanglement. This is a full entanglement. So every qubit is to entangle to the other qubit. You could have a linear entanglement. In that case, this would be entangled with this would be entangled with this would be entangled with this and over. If you had a circular entanglement, then this with this with this with this, and then from here to here another entanglement you would have. So a circular entanglement would be completed. And this is a reps equal to 1. You can do a reps equal to 2, 3, 4. Just one word of caution: as the deeper the circuits you make, the effect of noise. So in yesterday's class, you've already learned about noise. So the deeper the circuit you make, the effect of noise is more pronounced. Your qubit tends to go decoherent after a certain while. So decoherence errors also will come up and there are more issues. So shallow circuits typically are the things that are working very well in this NISQ era, right? Okay, so I just showed this code because I thought that there is some interest and there are some people who are interested in what is the classical post-processing that we could do on top of training these models. If not any questions, I would like to quickly cover this and then we can spend the last 5 minutes and some more questions. Okay. So what we are talking about is having a warm start model, and here I will also show you another thing that you can actually have integration. So Qiskit is very well integrated to different platforms, and that's the reason why Qiskit is so widely popular, right? So it is integrated with PyTorch and TensorFlow and all of this. So here we are actually going to see some PyTorch integration. Okay. So here we are also doing the same kind of model. So we are importing a VQC and we are doing some VQC. And here what we are trying to do is we are trying to get 2 backends. So this could be 2 hardware. So suppose you want to train it on hardware 1 and test it on hardware 2, or here they are training. You can do it training on air simulator and test it on a state vector simulator. So you can just consider this as backend 1 and backend 2. Okay, so here they are trying to prepare some data set, and whatever data set they are preparing, it is having it has 2 features, and so that's the reason you have this shape as 40,2. Let us assume that the 2 features are say the diameter of the ball and say the weight of the ball. Okay, I'm just giving examples here. So and they're using min-max scaler. So min-max scaler we are just trying to do because we want to scale down the features to 0 and 1. And then you have these features and then you transform these features to be able to better use it. And they are now plotting the first 5 features just to see, okay, they're scaled between 0 and 1 or not. So you see these features are scaled between 0 and 1. Now we used VQC, so we are now going to again just go back and use the same VQC. Now another thing that we are going to see here is VQC, typically the Y or the label vector in VQC is a one-hot encoding vector. I'm not sure if most of you know what is one-hot vector encoding. So if you have say 2 data points, so you will have 0 and 1. So at so if your data point x1, you can represent that as 1, 0 and that is belonging to class 1. And if your some other data point belongs to class 2, you can say that this is a 0, 1. Right, so you can have it. So if it is like n classes, so you will have what is the dimension of the vector would be n, and whichever that particular data point belongs to say n minus 1th class, so then n minus 1th point will become a 1 and rest all will be 0. So that's called a one-hot encoding. So VQC assumes that you have passing the labels as a one-hot encoding vector. So we'll have a one-hot encoding over our y-axis, and we'll convert our labels as well. So this is how our labels look like. So this 4 data points belong to the say the class 1, and the 5th data point belongs to our class 2. Okay, and then you're trying to split the data set. So in classical machine learning, we often do this. We have a trained data and a test data and a validation data, or at least we have a trained data and a test data. So here also they had 40 samples, and they are taking okay, they are calling it as a rule of thumb. I mean whatever, just ignore that and say that okay, here in this particular case we have 80% of the data that goes into training and 20% that goes into test, right? So your training sample is now 30 data, so you are passing this as your train size is equal to 30, and then this particular function, this is a train test split. Again, this is from your sklearn, so it's a classical function that you are using. Okay, so now you have been able to split your train data, test data and everything, and now you just plot it and see that okay, this is how your data set looks like. So this is typically how the other notebooks had the data. So now we have been able to arrange it in the same way. Here again you see that the solid ones are for the training and the hollow ones are for test. Now what are we doing? We are trying to train the model. So training a model is something that you guys already know. So max iteration. So suppose you want to use a Cobila and you just use say that okay, max iter is some value, and then you have some callback function wherein you are storing all the loss functions. So you have so that you can create a callback graph and see how the loss function looks like. And now we can use Cobila and create a circuit, create an ansatz, and then train this VQC. So VQC, what we need to pass is an ansatz, we pass the optimizer, and we ask it to give me back a callback, and we pass it what device are we running. So we are training the first model on a Qasam simulator. Okay, so when you train this model, you can actually see that this graph slowly it will populate this graph. Maybe I could have run all the cells. And we can see how it trains. So now let's train the model and let's see how it is training. So with every data point, you see that the loss function is changing. And right now the loss function is not going down, it just went up, down. So there's a lot of jitters, and eventually, and here one thing that we have set is just 20 iterations, right? So 20 iterations is too less. So we'll see that, okay, it is going to eventually stop at something, but we are still seeing good. So this was the starting point and it has dropped significantly. So it is here. But as we had expected, 20 iterations is very small, so it will not go. There's not a huge decrease. So from here to here, you have come down, right, in terms of your y-axis. And so that's what you see. And so now let's you can actually test it on your train data and test it on your test data, and you see okay, you're being able to do an 80% job. And now you want to save this model. So all you do is you have the .save function and you save this model, right? Now we want to load this model. We are trying to load the same model. So we are trying to load this VQC classifier model. and we just say that warm start equal to true. So this makes it, you know, very easy to train. It's simple English. And now you are saying that, okay, we are having a couple of things here. So we say that, okay, I want to retrain it on a different hardware, on a different simulator, whatever it is. But now I am increasing the number of iterations, and I realize that, you know, I have not trained it well, or sometimes there's a power cut and my model did not get trained well. But if you had it in your code that you were saving your model after every iteration, so even just before the power cut, that model would have got saved. So that would save you a huge amount of, you know, your experimentation time. And now you can just load from that last model that is saved and use do a warm start equal to true, and you can continue trading, right? So you can continue training, and this time we have given it more number of iterations. So now you see that this is continuing, and this is going to continue and try to decrease your loss function to some extent. And then we are again going to do the same things. We'll score it on the train data, and we'll score it on the test data, and we are going to see that, okay, are we being able to do any better than what we were doing earlier? So at least we see that, okay, from here to here we had decreased, and now we are going down a bit. So it is training, eventually it is training better. So had you had, say, because for to be able to do things faster, I had made this 20. So you can have this as 80, and then the next half could be even longer, and then you would actually see that the results are significantly getting better, right? So that's something that you can and let the training complete, and once the training complete, only then we'll be able to do the other cells. But just to show you guys, right? So from an 80%, you are actually now, the training accuracy has significantly increased to 933, but the testing accuracy is at 0.8. And one of the reasons you can say that, okay, now it is a flattish thing, so it is actually not doing any better on train, so probably it is overfitting on train, right? So it is overfitting on the train data. And in this time, at this point, you might also need to involve something called an early stopping or some other regularization parameter, wherein you can say that, okay, if for consecutive iterations the error is not decreasing further, then you stop it. Okay. So with that, I mean, there, you know, you can do the rest of the things, and but I'll just stop here, and we can spend the rest 5 minutes answering some questions. So stop sharing so that I can see the chat.
Yes, thank you so much. So I guess Kavita was asking a few times that how we can load data and do all of those things. Hopefully, Kavita, so that is fine with you now. How to load data and how to actually run QML circuit and things.
Okay, there's a lot of
Oh, sorry, Kavita.
yes,
Yeah.
yes. So,
Yes.
okay, Kavita actually said that, is it possible to show a working data set except the preloaded one? So yes, the last one that I showed you was a working data set. There are actually a lot of working data set codes that are available in GitHub and in the repository that you can also see. So in just, you know, we just created these toy data sets to be able to show you something very easily. It depends on you know, what type of application you do. I do a lot of finance applications, so I have a lot of finance data sets. Some people, I do a lot of image processing, so I have image data sets. But in every you know, as soon as you change the data set or you change the problem, what happens is the encoding mechanism, the loading data mechanism, everything changes, right? But these data encoding schemes remain the same. So whatever is your data, you can still use, say, Z feature map, CZ feature map, or raw amplitude encoding. So these are things that you have in Qiskit inbuilt, right? So a couple of those that I was going through in my handwritten notes. So you can just directly use as Qiskit functions. Okay, any other question?
I don't see any questions right now.
Okay, Rajul, I think the supervised quantum machine learning that I said was, yeah, Ritajit has mentioned, yeah, Maria and Petrushan. So that's, yes, that's the book. That's a book that's mostly concentrating on the supervised machine learning things. It does not have things like quantum clustering, quantum boosting, it does not have quantum k-means, it does not have the recent algorithms in the space of QGANs or quantum Boltzmann machine. There are tons of algorithms that are being developed. It is a very active area, very, I mean, a plethora of research papers that you get, and every other day I'm seeing a new research paper in terms of algorithms, of course, in terms of applications. So yeah, so you can start with that textbook, but I would rather suggest research papers is the right way to go there. Okay. Yeah, there's a large amount of material. Yes, I myself teach this for weeks in my course, but I hope that you guys got an intuition of each component, and whichever thing interests you more, you can probe into more details of that. Okay, then yeah, so thanks. Suritajit, over to you now.
Yes, I mean, I would really request if you can suggest them from where they can learn this hands-on, because that might be helpful for them, whoever is going for the hackathon.
Okay, yeah. So hands-on, I think that's the reason why I focused on this Qiskit machine learning tutorial in IQX. So if you go to your so let me again share my screen and show you guys exactly where I took these codes from. So if you go to Quantum Lab, you'll be able to see this. This is something that every one of you have. You go to lab files, you have Qiskit tutorials, and you go to Qiskit machine learning. You have all the codes here that you would need. The other good places is Qiskit Summer School 2021 that covered details about machine learning. Then there are other repositories in Qiskit. Okay, so let me post that link also on chat maybe. So it's called Qiskit Community Tutorials. Yeah. So Qiskit Community Tutorials is an excellent place where you have a large number of tutorials, so that you can play around with. Under Qiskit community tutorials also you have machine learning, wherein you have these codes. So let me just paste this link. Oh. Okay. Okay.
Okay, so
Thanks everyone.
I guess, yes, I guess we can thank Anupama for this wonderful session, for both taking both the lecture and the hands-on. We all learned a lot of things, and thank you so much for giving this much time to us.
Sure. Okay. Thanks, guys.
Yeah. So as for everyone else, I can stop the recording now.